So hello everyone and welcome back to a brand new video after so much time. So I had my exams in like last 2 weeks, so I was not able to upload anything. But from now on you can expect regular videos. So in this video I will be solving problem E, that is don't isolate elements, from Atcoder contest 283. I will also make a video on problem F, and later today there is also a Atcoder grand contest, so I will also try to cover some problems from that contest as well. So let's move on to the solution and let's see how we can solve this. So in the problem, we have been given a n cross m grid, right? And all of its entries are either a 0 or either a 1, right? And value of n and m can be up to 1000. So that means value of n into m can go up to 10 to the power 6. Given this, we have also been given an operation, right? In one operation, we can choose any row. Let's call it I, and you can flip all the values in row I, and you can flip all values in row I. And we want to apply this operation such that every number at least has one same neighbor, right? So if you think about element, let's say we call a element aij, then it has 4 neighbors. It has ai minus 1j, it has aij plus 1, it has aij minus 1, and it has ai plus 1j. And we want to apply operation on the grid such that my element aij should be equal to at least one of its neighbors, right? So we want to apply the operation such that for every element aij in the grid, right, aij in the grid, it should have at least one same neighbor. That is the problem. Or if it's impossible, you have to print out -1, right? So find the minimum number of operations that are required such that every element should have at least one same neighbor, or print -1 if it's impossible. So that is the problem. Now how can we solve this? So let's move on to the observations, right? The very first observation that we require is that you should not apply a operation on same row twice, right? Because like if we have some row, let's say ri, if we apply operation on this row, right, this will become some row ri dash, and if you apply the operation on this again, right, it will again become the row ri, right? So that is useless. If you apply the operation twice, it is just similar to like applying no operations. So for every row there are only two possible configurations, right? So for every row there are only two possible configurations, either ri where you like flip no values, or ri dash where all the values are flipped. So in total we have a n cross m grid. So we have n rows, right? We have r1, r2, r3, r4, so on up to rn. My row r1 has two configurations, r1 and r1 dash, where we don't apply an operation on r1 and where we apply an operation on r1. Similarly, r2 has two configurations, r2 and r2 dash, so on. Every row has two possible configurations. So in total we have 2 into 2 into 2, so on up to 2 n times, right? So in total we have 2 to the power n total configurations. So like if we talk about all the combinations that we can have, in total we can have 2 to the power n total combinations. But in the problem, my n can go up to 1000. So like it's impossible to go over all the configurations, right? Because 2 to the power 1000 is a very large number. So we cannot go over all the configurations. So now we have to somehow optimize this. Now how do we optimize this? And if you guys are not aware, this is a very standard use case of DP. So like for a future reference, you guys can think that we can reduce a complexity of a problem from O of n factorial to O of 2 the power n, right? So we can use dp to go from factorial complexity to exponential. Similarly, we can use dp to go from O the power 2n, that is from exponential complexity, to O the power n, that is linear complexity. But to apply this transition from O the power 2n to O the power n, my dp state, like that is dp of phi, should only be like dependent on like one or two states. My dp of phi should not be dependent on all the states from 1 to I minus 1, right? So I should be able to compute dp of phi either using dp of I minus 1 or dp of I minus 2. I don't have to like go over all the complexities from 1 to I minus 1, right? So that is the condition that is required to go from O of 2 the power n to O the power n. So my dp of I should be calculated just using one or two previous states. It should not be dependent on all the previous states from 1 to I minus 1. And if we look at this problem, it satisfies the condition, right? Because if we have, let's say, R1, R2, R3, R4, so on up to, let's say, Rn. And if we talk about any random row, let's talk about Ri. This Ri is only connected with Ri minus 1 and Ri plus 1, right? So my Ri is not bothered. My Ri is not bothered with Ri minus 2. It is not bothered with Ri minus 3, so on up to R1, right? So my Ri only cares about Ri minus 1 and Ri plus 1. So for every dp of I just need to keep track of these two rows, right? I just need to keep track of these two rows and I don't need to care about the previous rows. So that's why I can use dp here to go from O the power 2n to O the power n. Otherwise, the complexity, like if my Ri was bothered by all the rows from R1 to Ri, then my complexity would have been gone O the power n square, right? And this would have TL'd in the problem, right? So like this condition was important to go from exponential to linear. Otherwise, we could have gone from exponential to quadratic easily, right? So now let's see how we can define the dp, because that is the main part. So now let's start with the dp. So I can define my dp of I plus 1, and let's call it flag 1 and let's call it flag 2, right? So this will tell me the minimum number of moves, right, that are required such that my all the rows from 1 to I are satisfied. Here my flag 1 will tell me if my row I plus 1 was toggled or not, or you can say my row I plus 1 was flipped or not. And my flag 2 will tell me if my row I was flipped or not, right? So we have row I minus 2, we have row I minus 1, we have row I, and we have row I plus 1, right? So for this row, I will have flag 1. For this row, I will have flag 2, right? And my dp of I plus 1, flag 1 and flag 2 will tell me the minimum number of moves that are required to make all the rows up to this point satisfied, right? So that will be my dp state, and in the end your answer will be just minimum of dp of n, and here you can say all flag configurations, that is 0 0 0 1 1 0 1 1, right? So you will compute dp of n and then find the minimum among all the flag configurations. That will be your final answer. So now we know what our dp state is, but now the main thing is how do we make a transition, right? So now let's try to see the transitions. So for dp of I plus 1, flag 1 and flag 2, we will make a transition from dp of I, right? We will make a transition from dp of I. Now how do we make this transition? Let's see that. So this will tell me if my row I plus 1 is flipped or not, and this will tell me if my row I is flipped or not, right? So I have to use this flag 2 in combination with the row I minus 1. So like if we see the flags here, if we write the flags here my flag 1 will tell me if my row I was flipped or not, and here my flag 2 will tell me if my row I minus 1 was flipped or not. So like this here flag 2 is the value of like if row I was flipped or not, right? So like this value will carry over in dp of I, and we can iterate over all possible values of flag 2 here. So for my dp of I plus 1, flag 1, flag 2, iterate over all possible values of flag 1, right? Iterate over all possible values of flag 1. Similarly, iterate over all possible values of flag 2 and compute this answer using dp of I, right? Here this flag 2 is telling me if my row I was flipped or not. So I can use this directly in dp of I flag 2. And here this is the flag 3, where flag 3 will tell me if my row I minus 1 was flipped or not. So here you can also iterate for all possible values of flag 3 as well. Values of flag 3. So now we have something like this. Now we have row I minus 2, we have row I minus 1, we have row I, and we have row I plus 1, right? So we have 3 flags. We have flag 1 here, we have flag 2 here, we have flag 3 here, right? So now we know the value of all of these flags, right? We have iterated over all the possible values. We know the value of flag 1, we know the value of flag 2, and we know the value of flag 3. So here you can just check, right? Using these 3 values, you can just check if your row I is satisfied or not. Your row I is satisfied or not, right? Because your row I will have some elements. We will have AI0, we will have AI1, we will have AI2, so on up to AIM, right? There will be row I minus 1. On top of this, there will be row I plus 1 under this. We know if like this row was flipped or not, we know this row was flipped or not, we know this row was flipped or not, right? Then for every element in row I, you can check if it has the same neighbor or not using the top row, bottom row, and its neighboring columns. Check if every element has a equal element or not, right? So check this, and like if you're not like if you find an element who does not have a same neighbor, then just set your answer to infinite, right? That means the answer is impossible, or you can say it takes infinite moves for this configuration, right? So like that is the entire theme, or you can say that is the entire structure of the dp, how dp will work. So for every possible value of flag 1, flag 2, and flag 3, you have to compute dp of I plus 1 using dp of I. When you know the value of flag 1, flag 2, and flag 3, like you can compute if your row I was satisfied or not. So like iterate over all the elements in row I and check if row I is satisfied or not. If it is, then update your dp of I plus 1. Otherwise, like keep your dp of I plus 1 as infinite. That means like the row I was not satisfied, or like you have to make infinite moves in this case, right? So that will be the entire solution. If like you have to see the pseudocode will be something like for every flag 1 in 0 and 1, for every flag 2 in 0 and 1, and for every flag 3 in 0 and 1. You will check if you're like flip rows I minus 1, I plus 1 accordingly to the flags, according to flags. Then go over all the elements in row I. So for 0 up to m minus 1 in row I, check if element has same neighbor or not. And if it has, right, and if all the neighbors all the neighbors have same elements. Then update your dp of I plus 1, flag 1 and flag 2 using dp of I, flag 2 and flag 3, using dp of I, flag 2 and flag 3. And in the end your answer will be, in the end your answer is just minimum of dp of n and all possible flag configurations, all possible flag configs. So that will be the entire solution. And if you guys want to see the code for this, so here's the code. I will first take my grid as the input, then I will define my dp and my base dp cases. Here my dp of I plus 1 j, k will represent the minimum number of moves that are required to make all the rows up to I. Okay. Here j is like if row I plus 1 was flipped or not, and k will tell me if my row I was flipped or not. Then I will iterate over all the values of flag 1, flag 2 and flag 3. So here j is my flag 3, it will tell me if my row I minus 1 was flipped or not. My k will tell me if my row I was flipped or not, this is flag 2. And my L is my flag 1, it will tell me if my row I plus 1 was flipped or not. So then I will iterate over all the elements in row I, because I have to check if my row I is satisfied or not. So I will go for y equal to 0 up to m. I will iterate over all the elements in row I, and for every element I will check its top neighbor, its bottom neighbor, its left neighbor and its right neighbor. If like all of the neighbors are different, I will set my OK equal to false. Like it will tell me I have to ignore this dp state. So if my OK is equal to false, I will ignore the dp state. Otherwise, if my OK is equal to true, that means all the elements had some same neighbor. Then I will update my dp of I plus 1. Here L is my flag, here L is my flag 1. So I will update dp of I plus 1, flag 1, flag 2 with dp of I, flag 2 and flag 3. Here L will tell me if I have to add the extra move or not, right? Because if my like row I plus 1 was flipped, then I will have to add an extra move. So my flag L will tell me if I have to add the extra move or not here, right? So that is why I am adding dp of I k j plus L to tell me if the extra move or operation was required to flip row I plus 1 or not. And in the end, you can just go over all the possible combinations or configurations of your dp of n. And like if your answer is equal to infinite, that means there was no possible move sequence to make the grid good, then just return false. Otherwise, you can print out your answer. So that will be the entire solution. And if you guys have some doubts, feel free to join my Discord server. I'll be more than happy to answer your doubts there. And I will see you guys in the next one. Bye-bye. But before we move on to the solution, I want to tell you guys about Newton School's coding contest. As you guys know, Newton Schools does this coding contest every month. And this month, the name of the contest is Code Rush X, and the prizes are better than ever before. So you can win prizes up to rupees 10 lakhs. And along with this, you can win placement opportunities in top product companies. So like if you guys want to play this for fun or you guys want to play this for placements, that is totally up to you. The contest will be on 28th of January. It will start around 9 p.m. and the contest will be 3 hours long. So there will be ample amount of time for you guys to brainstorm and solve good quality problems. So if you guys want to benchmark yourself or just win some placements, this is a very good opportunity. I will leave a link to this contest in the comments and in the description, so you guys can go and sign up from there and show, or you can flex how good you are at problem solving. So now let's move on to the solution.